Hello DSci 2000. In this video, I will be covering more data manipulation in R. Here's the usual objective slide. Please pause and read before proceeding. So we're going to ignore this for the most part. What we're going to do is we're just going to take our R Markdown file from the prior lecture and just build from it. I'm going to open up my DSci 2000 folder, open up the rproj file, and here, I already have my R Markdown file open. If you don't have it open, you can go to the bottom right, click on Unit 5, and just click on your R Markdown file right there. Let's go ahead and scroll all the way down and add a new section right here. So we're going to start off by renaming columns. In this slide, I demonstrate how to rename an ID column and change the ID column to have the new name new ID and back. Let's explain how this works. Here I'm going to title the section renaming columns. So at this point, I don't want to reread in the CSV file that I had read in earlier in the last lecture. So here's what I can do. I'm going to put my cursor just after this renaming columns section. Then I'm going to scroll up and I'm going to click this arrow right next to run. Once you're here, just click Run All Chunks Above. This will execute all chunks of code that occur above your cursor. And you can see that R Markdown will, by default, spit out the output of each of those lines of code inside the file. If I scroll down, my cursor is still there. Let's go to the right. The data frame is there. So the data frame has been read in. Let's just remind ourselves of what's in this data frame. Let's click on DF. And I want to consider the following problem. Let's change this ID column to new ID. Here's how you do that. First, what I'm going to do is I'm going to add in an R code chunk. Just after renaming columns, make sure you have a blank line in between. And I'm going to do call names df, call names df equals ID, and set it to new underscore ID. So what is this doing? This is renaming the ID column to new ID. Let's explain what this code is doing. This is saying this. Take the call names df vector and filter using the Boolean method. What do I mean by this? I have a vector, then I have a bracket with a condition inside it. This is just one-dimensional Boolean filtering. In the last video, I discussed two-dimensional data frame filtering. One-dimensional filtering is the same thing in that you start with a one-dimensional vector, the column names of df, you have brackets, and then you put a condition in there for filtering. So this is just like how it is for data frames, except in this case, since we're filtering a vector, we don't add a comma after this. So in essence, what this is doing is this is saying, take the column names of df, filter the column names of df for any column names that are equal to ID, and then set those components of the vector equal to new ID. So this is how in base R, you rename the ID column to new ID. You use the idea of Boolean filtering to filter on a vector. Let's press Ctrl Enter to execute this code. Now let's go to df. You can see here that ID is now new ID. Now, let's change new ID back to ID. Just copy and paste those lines. And now we just have to change our filter to look for components of the vector that are equal to new ID and switch them with ID. Press Ctrl Enter, and let's look at our data frame df, and now it's back to ID. So that's the first data manipulation task I want you to know how to do in base R, which is how to rename a column name. It's just this idea again of just Boolean filtering, except instead of two-dimensional Boolean filtering by rows, like I showed you in the last video, this is just one-dimensional Boolean filtering with a vector. The next data manipulation operation I want to tell you about is selection of particular columns. Let's add this section to our R Markdown file. I'm going to add in an R code chunk. And let's say, for example, I want to select only the year and salary columns of DF. How do you do that? How you do that is this. First, I'm going to wrap head around my output so it doesn't print the entire thing. And I'm going to take DF and again execute a Boolean filter, except on the column index, because there are particular columns that I want. And what I'm going to do is I'm going to throw in a condition for filtering, just like we have been. So I want to look for all call names of DF that are in the vector year or salary. So to select particular columns, you just use Boolean indexing again, except you throw the condition in the column index because there are only particular columns you want. Let's go ahead and scroll up and hit knit. If I scroll down on this document, I can see that what this code has done is it has taken DF and it has only shown me the year and salary columns. I hope by this point it is very clear why understanding how Boolean indexing works in R is very important. You might be wondering why at this point, why I haven't thrown which around any of these Boolean filters. The reason why I haven't done that at this point is because I am not worried about any of my filtering resulting in NA values. For example, with this condition, call names of DF equaling ID, I am not worried about any of the column names of DF being NA. That just won't happen. Because in R, column names must have a specific value. They cannot be NA. Similarly, that's also why I'm not worried about throwing which around here. Because, again, none of the column names of DF are going to be NA. So I am comfortable just throwing in the Boolean filter without which here, because I know that no column name in R can be NA. When I am doing row index filtering, like I did in the last video, I would want to apply which to my filter. So in case you're wondering why I'm not doing which around these Boolean filters, it's because I'm not worried about any of those filters given my knowledge of R resulting in an NA condition. The next thing I want to discuss is filtering for unduplicated values. Let's say that I want every combination of race and sex in the DF data frame. Here's how I would do that. I'm going to add in an R code chunk. And what's very nice is that in this situation, I can just use unique. Unique does not only have to be used around a vector, it can be used in a data frame as well. And so I'm aiming to get the unique combinations of race and gender in the DF data frame. So how I would do that is I would wrap unique around DF and only select the column names of DF that are in the vector race and sex. So what this is doing is it is showing the unique combinations of race and sex in the data frame. Let's hit knit. Now if I scroll down, I can see that what this has done is it has given me every possible combination of sex and race that exist in the data. So this is just combining Boolean filtering with what I showed you on how to select particular columns. And then you just wrap unique around it. Let's talk about creation of new columns. Another phrase to just describe what I'm doing is called the creation of a calculated field. So here's how you would do that. So in this example, so at the time I wrote these slides, to convert from US dollars to Canadian dollars, I had to multiply US dollars by 1.33. This is an example of a calculated field because salary Canadian depends on the value of a different column. So this is how you create a calculated field in R called salary Canadian, which is 1.33 times the salary in US dollars. Let's go ahead and do this in our code. So we are creating a new field called salary Canadian, which is 1.33 times the salary in US dollars. Let's add in our code chunk. And what I'm going to do is I'm going to refer to the DF data frame, $, and I'm going to add in the new column name, salary underscore Canadian. And we're going to make that 1.33 times DF $salary. And let's just do head on DF, just so we can see what DF will look like now that we have the salary Canadian column added to it. Let's hit knit. Now if I scroll down, I can see now that the salary Canadian column has been added to DF. So this is how you add a new column in a data frame. You just use the data frame with a $, with the new column name, and you set it equal to a particular value. In this case, salary Canadian is a calculated field because it depends on another column. So salary Canadian was a very simple calculated field in that you could apply this formula uniformly throughout every single row. It would just be 1.33 times whatever is in that row's corresponding salary value. However, there are going to be some situations where the formula is not going to be the same for every single row. I will let you do this one on your own, but for example, if you wanted to figure out the US tax rate at the time I wrote these slides based on the salary, you would have to first initialize a tax rate to NA, and then you would have to use Boolean filtering with corresponding values to assign an appropriate tax rate, as you see here. For example, once I've initialized the DF tax rate to NA, it's going to make the entire data frame NA for the tax rate column. And then once I execute this first line right here, what it's going to do is it's going to say this. Look in the tax rate column. If the salary in the corresponding row is less than 9,526, make the tax rate 0.1. And it will do this for every other condition here. I'm not going to do this because this is going to be a lot of typing, but I strongly suggest that you do this on your own. So you have to do this when the values are going to change depending on a Boolean condition. In this situation, I might want to be a little careful and add which around these Boolean filters because there might be NA salaries in here. However, I can tell you that in this data set that none of the salaries are NA. So that's why I didn't worry about adding which around these Boolean filters. And if you do that, you can see that the tax rate has been added to the right part of that data frame. So to begin our discussion on how to sort a data frame by rows based on the values of a column, we have to discuss the order function. The order function, what it does is it takes in a vector, such as what you see here, 14,850, and it by default returns the indices of the corresponding values so that the vector that you give the order function would be in ascending order. For example, the output of this function right here is 213. This is indicative of the fact that if I were to order 14, 8, and 50 in ascending order, the 8 would be first, the 14 would be second, and the 50 would be third. Those correspond to indices 2, 1, and 3. By default, order uses ascending order. If I wanted to, I could add the decreasing equals true argument to the order function to get the corresponding indices of what I give the order function, except in decreasing order. So in descending order, this vector would be 50, 14, and then 8. So those correspond to the third, first, and second indices, because that is how that vector would be written in descending order. Using indexing, again, I can just throw those indexes inside the bracket for filtering to get a vector in ascending and descending order. So in this situation, I want to order 14, 8, and 50 in ascending order. What order does, as I showed you in the last slide, is by default, it would give me the indices of the corresponding vector if I wanted to order the vector in ascending order. By doing this, I get 8, 14, and 50, which is 14, 8, 50 in ascending order. If I do the same thing with decreasing equals true, I will get 50, 14, 8. So again, it's using this idea of indexing to filter indices, except in this situation, for a specific order that we want the vector to be returned in. We can then apply this concept to order a data frame based on rows. In this situation, what is happening is that the data frame is ordering by year and then by salary in descending order. So what this is doing is it's saying this: take the data frame, order the rows so that they are in descending order by year, and then once you've finished that ordering within a particular year, order the salaries in descending order. So we can see here, for example, that in this excerpt of this data frame, that salaries are in descending order. Let's go ahead and do this in our code. So we're ordering a data frame based on the values of columns. So we want to order DF by year and then by salary in descending order. Let's add in our code chunk. And what we're going to do is this, DF, and we're ordering the rows based on this. So we need to throw this in the row index. Order DF $year, DF $salary, decreasing equals true. Let's wrap head around this so it doesn't print out the whole thing. And let's hit knit. And you can see here that this output is identical to what I showed you in the slides. One disadvantage they need to be aware of with order, which we will remedy later with dplyr, is that order requires that with all columns that you give it, that they're either all increasing or they're all decreasing. In this situation, we wanted to order by year and then by salary. By adding decreasing equals true, we required both year and salary to be in decreasing order. We could not, for example, make year in increasing order, and then salary in decreasing order. With the order function in base R, all of the columns you feed it must either all be increasing or all be decreasing. And we will remedy this problem once we discuss dplyr. The next thing I want to talk about is aggregation. Aggregation is just a fancy word referring to computing summary statistics spanning multiple observations of data. Things like mean, median, mode, sum, or standard deviation. A question you might get from a manager might be something like this based on this data. What is the average salary of a person over every calendar year that's in this data? Here's the corresponding code you would use to do that. Let's go ahead and do that in our code. Add in another section. Average salary by year. So ordinarily, how you would do that is you would use the aggregate function. Salary, which is what you want to be computing the average of. And then I'm going to type in this tilde. It's shift with the key to the left of the 1, and then year. And I'm going to set data equal to df and fun equal to mean. df is the name of the data frame that I'm computing the average salaries for, and fun refers to the function that I want to apply on salary, which is the mean function which you use to compute averages. Let's go ahead and hit knit. And here's what it gives us. It gives us the years as well as the average salary over each year. However, here's one thing I want to let you know about. I get personally very annoyed at the fact that aggregate does not allow you to change those column names very easily. For example, I probably want to call salary average salary rather than just salary to be indicative of the fact that it is the average salary for every year. So going back to the slides, what you have to do beyond that is you need to apply the set names function around that aggregate input, and then use the aggregate output as the first argument of set names, and then whatever you want to change the column names to, you have to put in as a character vector in the second argument. So in this situation, I'm just taking the aggregate output that I just showed you in our markdown, and I'm now changing their column names to year and mean salary. Let's go ahead and do that here. I'm going to copy and paste these lines of code. Make sure you have a blank line, paste, and we're changing the column names to year and mean salary. And all you're doing is you're doing set names with a capital N, the aggregate function we just did as the first argument, and then a character vector with year and mean underscore salary as the second argument. Let's go ahead and hit the knit button. And scrolling down, we can see that instead of just year and salary, now we have year and mean salary, which are column names I prefer for this situation because these are not just salary values, they are average salary values. Now let's say I wanted to add another level of aggregation. What if I wanted average salary over each year and by sex? Going back to our markdown, what I'm going to do is I'm just going to copy and paste these lines of code. Make sure you have a blank line right there. And I'm doing average salary by year and sex. All you would do is you would add a plus sign right next to year because it's another level of aggregation in addition to the year. So the next thing I have to do is I have to add in a name for the sex column. The sex column is going to go after year. So I'm going to add that in as a character right here. I'm going to hit the knit button, and I can see now we have mean salary by year and by sex. Let's say I wanted to add another level of granularity to this. Let's say I wanted average salary by sex and year for Asians only. What that amounts to is just the same function, except I'm filtering the data frame for only records for which the race is equal to Asian. This is the construction I showed you in the last lecture. Let's go ahead and do that. I'm just going to copy and paste those lines of code, and add in a blank line, and I'm just going to change this to df, where df $race equals Asian. Don't forget the comma to indicate that that's a row index. And because this line of code is getting pretty long, I'm going to press enter just to separate this over multiple lines. And this is for Asian records only. Let's hit knit. And scrolling down, this is the same type of summary statistics as I showed you up here, except these are for Asian records only. And that's all I have for you in this video. First of all, make sure you've saved this R Markdown file. If you haven't saved it, make sure you just hit the knit button. I'm going to close this out. Make sure you hit don't save. And then in my DSci 2000 folder, I'm going to hit git bash here. I'm just going to do a commit because we've already committed this file in the past, and just say something like finished more data manipulation in base R. Let's just do a push, and that's all you need.